Okay, so now that we have more than two stereocenters, let's start keeping track of our stereoisomers. Okay, so if we have two stereocenters, that means we're going to have two pairs of enantiomers. And so one pair of enantiomers is going to have a non-superimposable mirror image. The other pair is going to be a non-superimposable mirror image, but these two things are not going to have mirror images of each other. Okay, so let's look at what that looks like in the sense of, in the structure of trihydroxybutanal, which is an aldehyde with three hydroxides on it. Okay, so if we drew the compound in one isomer here and just arbitrarily picked it such that we had these hydroxides were both on the same side, and then we drew its mirror image, those hydroxides would start from the middle, and then we have our aldehyde group is still going to be at the top, our alcohol group is still going to be at the bottom, and these hydrogens are going to be sticking out the sides here. So you should be able to convince yourself that those are mirror images of each other and that they're non-superimposable. The fact that their mirror image is non-superimposable, that's our first pair of enantiomers. Okay. So the only way to make another isomer here, if we just did mirror images of these again, that would be the same two compounds. So in the other isomer we've drawn here, we've swapped it so these hydroxides are opposite each other. These alcohols are opposite each other. And when we do that and we draw the mirror image of it, they're still opposite each other. And so this is the mirror image of that, which makes this a pair of enantiomers. But these don't look, this set looks different than this set. These are not superimposable sets, okay? So this non-superimposable mirror image is one pair of enantiomers. This non-superimposable mirror image is the other set of enantiomers, but the pair of those two sets of enantiomers is our diastereomer set, okay? So we had to actually exchange the connectivity between the two different systems to be able to get all four isomers available to us. Okay, so once you start adding a second stereocenter, you have the possibility of creating an achiral compound by creating a mirror plane inside the molecule. When we first started talking about pairs of enantiomers, we looked at mirror images outside the molecule, where we have a molecule, we add the mirror, and then we look at the mirror image. In the case of a meso compound, if you can find a mirror plane inside the compound such that they have a superimposable image within itself, see how this looks like that, this looks like that, and this looks like that, okay? We now have a mirror image inside the molecule. If we have a mirror image inside the molecule, that means that it is superimposable. And if it's superimposable, that means it is not chiral. It has a mirror image. We drew the mirror image over here, but because the mirror image has that same plane, we actually can superimpose those two images. That means this isomer of the diastereomer set is actually not chiral. So that means this pair of enantiomers are chiral. This pair of compounds actually is the same compound because it's now superimposable because of the mirror, and it becomes a meso compound. And it is not chiral. Okay. The whole reason this happens is because we found a plane of symmetry. Okay. When we talk about mirror planes, we are talking about outside the molecule. Planes of symmetry are imaginary planes passed through the molecule. They can be, like in the case of this compound here, we actually have a plane of symmetry going between the hydrogen sticking back and the OH sticking forward, and the methyl groups on both sides are mirror images of each other. So when we drew that first compound where we had isopropanol, it was achiral. It didn't have four different groups, and that's because it allows it to have this plane of symmetry inside the molecule. Now, these planes of symmetry can be in any direction. They can be including two or more bonds of the compound. It can be actually outside or in between two atoms. So they can actually encompass atoms or be in between atoms. In the case of this compound right here, the plane of symmetry goes through the hydrogen, the carbon, and the oxygen out here. In the previous one, the plane of symmetry goes in between these two carbon bonds. Okay, so the plane of symmetry doesn't have to go through atoms, but it does have to go through at least a bond to see the plane of symmetry.